Now let us look at the next problem. An insulated container of gas has two chambers separated by an insulating partition. One of the chamber has a volume V1 and contains ideal gas at pressure P1 and temperature T1. Okay, so you have a insulated gas chamber or container which has got two chambers. Okay, so in one you have pressure P1, volume V1 and temperature T1. The other chamber has a volume V2, contains ideal gas at pressure P2 and temperature T2. So the other chamber has P2, V2, T2. If the partition is removed without doing any work on the gas, the final equilibrium temperature of the gas in the container will be. Now when we remove the partition, what will happen is that now it will attain a common pressure. Now the total volume will be V1 plus V2 and it will attain a common temperature T. That means all the gas molecules of first chamber and that of the second chamber, they are mixed thoroughly. But there is no loss of energy to the surrounding because this is an insulated chamber. And while removing the partition, there was no work done on the gas, work done by the gas. So it gives you an idea that total internal energy of the system will remain conserved. Okay, now we know that internal energy delta U will be 0 for the total system. So that means internal energy of the first gas in the chamber, internal energy of the gas in the second chamber will be equal to the final internal energy of the combination. Okay, we also know that internal energy is a function of temperature. Okay, and for ideal gas, PV is equal to nRT. So when we say internal energy is not going to change, it basically means that P1 V1 plus P2 V2. Now this P1 V1 and P2 V2, their indication of two things. One is that internal energy, total energy is not going to change. Second, there is no work done on the gas. This is equal to the common pressure P and the volume V1 plus V2. Okay, so this is one finding that we can write based on the statements that are given. Second thing is, for the first gas we can write N1 RT1 is equal to P1 V1. So the number of moles is equal to P1 V1 upon RT1. Okay, and number of moles in the second gas will be equal to P2 V2 upon RT2. Okay, now the final temperature will be given by T, and the ideal gas equation for the combination now can be written as N1 plus N2 times R T. Now this is the common temperature is equal to common pressure P and total volume is V1 plus V2. Okay, now P V1 plus V2 can be replaced by P1 V1 plus P2 V2. Okay, so P1 V1 plus P2 V2 is equal to N1 plus N2 RT. Okay, now this N1 plus N2 R can be written as P1 V1 upon T1 plus P2 V2 upon T2. times T is equal to P1 V1 plus P2 V2. Now we just need to solve to get the common temperature T, which will be equal to P1 V1 plus P2 V2 divided by P1 V1 by T1 plus P2 V2 by T2. Now this can be further written into as T1 T2 times P1 V1 plus P2 V2 upon P1 V1 T2 plus P2 V2 T1. Okay, so this is the final temperature